Okay, good morning, everyone. Okay, welcome to the calculus class. And we were talking about the trigonometric substitution. And let me mention a few more things today. Okay, so first of all, let me show the notebook. Okay, sorry. Okay, so there are three types of substitutions. Okay, first of all, if you see, okay, so inside the square root, we have some number plus or minus x squared. So if you see the negative sign in front of x squared, okay? So if you see negative sign in front of x squared, then you need to replace x with a sine theta, okay? So x will be replaced by a sine theta when you see negative sign in front of x squared. Now when the in front of x squared, if you see the plus sign, there are two types. When positive number and x squared are added, as in the second case, so some positive number a squared is added, okay, with x squared, then you will replace x with a tangent theta. But if you see the plus sign in front of x squared and then you see some minus positive number, okay, then you replace x with a secant theta. So there are three types. Okay. So in example 1, we see the negative sign in front of x squared. Okay. So that's why we introduce 3 sine theta for x. I mean, x is replaced by 3 sine theta because there is a negative sign in front of x squared. And at this point, the 9 corresponds to a squared. So that means a will be 3. So x is replaced by 3 sine theta. That's what we did in example 1. Now in example 2, okay, we considered certain integration here, down here, and you see negative x squared. So we replace x with a sine theta again. Okay. Now, in example 3, we see the plus sign in front of x squared, and some positive number 4 is added. So in that case, this positive number will be your a squared. So that means a will be 2, and x is replaced by a 2 tangent theta. Okay, so x squared plus some positive number. So in that case, that positive number is your a squared. Okay, and then in example 5, we see x squared minus a squared inside the square root. So x will be in this case replaced by a secant theta. If x is a secant theta, then the x d theta will be a secant theta tangent theta, so that the x will be a secant theta tangent theta d theta. Okay? So if I replace x with a secant theta, then by some calculation as we did the other day, square root of x squared minus a squared will be a tangent theta. and dx will be a secant theta tangent theta d theta. So if I plug in those two into the integration, then we get the integration of secant theta d theta, which will be the natural log of secant theta tangent theta plus c. Now, as I said, this is not the end of the calculation because initially I give some problem which requires the integration in x variable. So I anticipate a certain expression in x, not theta. So I need to go back to my previous variable x from theta. So how can I handle this? Since secant theta, x was a secant theta, secant theta will be x over a. If then when I draw the right triangle with angle theta here, then when secant theta is x over a, then that means hypotenuse will be x and the adjacent will be your a. If the hypotenuse is x and the adjacent is a, then the Pythagorean theorem says the opposite will be square root of x squared minus a squared, right? So you remember this Pythagorean theorem saying if you have, say, the adjacent is a, the opposite is b, and hypotenuse is c, then we know that a squared plus b squared will be c squared. That is the very important property from the right triangle, right? Which is called the Pythagorean theorem, right? So if I have this right triangle, then this a squared plus b squared will make c squared. That is well-known equation. So if I use that property, then when the hypotenuse is x and the adjacent is a, then the opposite will be the square root of x squared minus a squared. Now in that case, we can easily replace. So previously we have log secant theta plus tangent theta. So secant theta plus tangent theta was inside the square root and absolute value, and then we take the log function here. So that's what we get. And secant theta is x over a. So secant theta is just x over a. And when the opposite is the square root of x squared minus a squared, tangent will be the ratio between the opposite and the adjacent, which will be the square root of x squared minus a squared over a. So that is your tangent. Then I can easily replace this secant and tangent theta in terms of x variable. So you can leave it this one like this. Or since both terms are inside this absolute value, the denominator is a. So we have x plus square root of x squared minus a squared over a plus c. And we know one, in that case, then I can split the log function by the difference between these two logarithmic functions, right? So log the numerator minus log denominator plus c. So here a is positive, so I don't need the absolute value for a, right? Originally it was log absolute value of a, but since a is positive, I can safely eliminate that absolute value sign and we get this expression at the bottom. And as I said, if you want, you can derive up to this or you can stop here. That would be fine as well. So that's what we considered the other day, right? And in this problem, in this problem, sometimes people may consider a slightly different substitution. Instead of a secant theta, people may introduce this substitution in terms of hyperbolic function. So when x is replaced by a the hyperbolic cosine of t, then the square root of x squared minus a squared, this one, will be square root of a hyperbolic cosine t total squared minus a squared. That will be a squared hyperbolic cosine t squared minus a squared. So a squared is common. So if I combine this with a squared, then you get a squared times hyperbolic cosine t squared minus 1. And hyperbolic cosine t minus 1 is hyperbolic sine t squared. So if I eliminate this the square root sign, you get just a hyperbolic sine t. So that corresponds to the square root of x squared minus a squared. Now, if x is replaced by hyperbolic cosine t, then what is the dx dt? That will be a hyperbolic sine t. So dx will be a hyperbolic sine t dt. So that corresponds to dx, and the square root of x squared minus a squared corresponds to a hyperbolic sine t. So if I integrate this term, then dx will be replaced by a hyperbolic sine t dt. Excuse me. Yeah. And the square root of x squared minus a squared will be a hyperbolic sine t. Now, a it can be cancelled and hyperbolic sine t can be cancelled. So the integrand will be just 1. So if you integrate 1, so here the integrand is 1. So if you integrate 1 with respect to t, then you get t. So you get t plus c, okay? But that is introducing a dummy variable t. What I want is as I said multiple times, I want some expression in terms of x variable, not t. So from this expression, replaced x with a hyperbolic cosine t. So hyperbolic cosine t will be x over a, right? Now, what is hyperbolic cosine t? That is e to the t plus e to the minus t over 2. That is x over a, right? So, okay, well, actually, yeah, right? So this is your x over a. So let me write it down here. So I want to replace the t with respect to x, but as I said, e to the t plus e to the minus t over 2, that is hyperbolic cosine t, and that is x over a. Okay? And I want to express t in terms of x. So the idea is this. Let me multiply 2 to this equation. Then we get e to the t plus e to the minus t equals to 2x over a. Okay. Now let me multiply e to the t to both sides of the equation. Then when e to the t is multiplied to the left hand side, you get e to the t squared plus 1 equals to 2 times of x over a times e to the t. So for temporarily, let me replace this e to the t by capital T, I mean uppercase T for simplicity. Then we have t squared, and then if I move this term to the left hand side, we get minus 2 times of x over at plus 1 equals to 0. So t will be by the quadratic formula for this second order equation, t will be 2 times of x over a plus or minus square root of x over 2x over a squared minus 4 over 2. Okay. So if I cancel 2 from the numerator and denominator, we get x over a plus or minus square root of x over a squared minus 1. Okay. Do you follow me up to this? Now, what is t? That is e to the t. Okay. Now, I know that e to the t is positive. Right? And e to the t, yeah, e to the t is positive. Just a second. Let me see. Did I make any? I b squared minus b plus or minus b squared minus, oh yeah. Now, the, why? Oh, right. Since this is the exponential function, and when t is positive, right? So t must be positive. So hmm, just yeah. So I cannot take this negative sign here, but only the positive sign. So e to the t must be x over a plus square root of x over a squared minus 1, or 1 is a squared minus a squared, right? So we have this. So that is your e to the t So if you want to find t here, then you need to take the log function on both sides. Then we get the previous expression. Okay. So even though you have the inverse of hyperbolic cosine of x over a, that seems to be different from our previous result, but actually it is identical. They are identical because my e to the t is can be written by this. So the expression in the equation 2 and the expression in expression 1 are identical. Okay, they are the same. But anyway, so in example 5, you may substitute hyperbolic cosine t for x if you want, okay? So if you want, you can do that. But the one demerit is that you need to do some calculation as I did here on this slide to derive the expression in expression 1. Okay? Do you follow me? So this expression here, that is not that I mean intuitive or straightforward. So so if I give this problem in the final exam, then both approaches are fine, and you can leave the expression as in the expression number 2 with the inverse of hyperbolic cosine of x over a if you want, or you can use the classical approach to derive the expression as in expression number 1. Okay, either is fine. Now, before we go to the next slide, let me mention one more stuff. Okay, so here for this problem, I considered x equals to a secant theta. That's what I used, okay, for this problem. But what if I consider a different approach? So one of the mistakes that students frequently make for this example is that since I have some number minus certain something, okay, and some students in the past substitute x with a sine theta. Because I mean some students just to focus on this negative sign, and when you see this negative sign, they automatically introduce x equals to a sine theta. But okay, you shouldn't do that. Okay, you should check the sign of x squared first. Okay, so if the sign of x squared is negative, then x will be replaced by a sine theta. But if the coefficient of x squared is positive, as in example 5, then you have two possibilities. Okay, so x squared plus some number squared, or some number squared plus x squared, then so this is very important. Okay, so if you see negative x squared, then x will be replaced by a sine theta. If you see square root of a squared plus x squared, or square root of x squared plus a squared, so two positive terms are added, then x will be replaced by a tangent theta. Now, if you see x squared minus a squared, then you must replace x with a secant theta, or the hyperbolic cosine t, that is fine, okay, but people usually consider secant theta. Anyway, if I make a mistake and if I introduce a sine theta for x, then x squared minus a squared will be a sine theta squared minus a squared. So you get a squared sine theta squared minus a squared. So a squared is common. So we get sine theta squared minus 1. Now, sine theta squared plus cosine theta squared will make 1, right? I mean, sine theta squared plus cosine theta squared makes 1. So if I subtract 1 from sine theta squared, what do I get? You get negative cosine theta squared. Then we have a problem because everything here is inside the square root sign. Okay. Then we get negative a cosine theta squared inside the square root. And we have a problem because this a cosine theta squared will be always non-negative. And if I have negative sign, then I need to consider some complex number, right? So, so if you face such negative value inside the square root, then that shows that you made a mistake at a certain point. I mean, usually your substitution was wrong, and you need to consider a different approach, different substitution. Okay. So you should have something positive inside the square root. Otherwise, you made a mistake. So please be careful. One more example here. Now I have plus sign plus 4 in front of x squared plus 9, and these two positive numbers are added. Okay, and okay, then this 9 seems to be a squared. So then shall I reintroduce x will be 3 tangent theta? No. Why not? In the table, I had x squared plus 9, not 4x squared plus 9, right? So please note in this case that you have 4, not 1 in front of x squared. So what you can do is you need to take this 4 out of this. So the point is, so there are two approaches at this point. So approach 1, you can take you can remove 4. How? Well, 4x squared plus 9 will be 4 times x squared plus 9/4. So if I take 3/2 power to this expression, then I have 3/2 power of this. So that means 4 to the 3/2 times x squared plus 9/4 to the 3/2. Okay. And what is 4 to the 3/2? 4 is 2 squared. So if I take the 3/2 power, you get 2 to the 3, which is 8. Right? So in that case, the expression, then this expression will be the integral of x cubed over, and the expression in the denominator is a times x squared plus 9/4 to the 3/2 dx, and the integral domain is from 0 to 3 square root of 3 over 2. Okay, or 1/8 times 0 to 3 square root of 3 over 2 x squared plus x squared plus 9/4 to the 3/2 power dx. So now I have x squared plus something squared, right? So in that case, your a squared will be 9/4. That is your a squared. So what is your x? X will be a tangent to theta. So a is the square root of 9/4. That is 3/2 tangent to theta. Okay. So that is one approach. You can take you can remove this number in front of x squared somehow. Okay. So that is one approach. Now in the slide or in the textbook, the authors are introducing a second approach. The idea is, so that is your first approach. Okay. The second approach is the following. Please note that, first of all, the 3/2 power of 4x squared plus 9 is cubic power of this square root term. So you see the square root of some 4x squared plus 9, and this square root of 4x squared plus 9 is not one of the expressions in the table of the previous slide, but it becomes one of them if I introduce u to represent 2x. Then 4x squared will be u squared. So square root of 4x squared plus 9 will be square root of u squared plus 9. And in that case, your 9 is your a squared. So u will be 3 tangent theta. Right? So, okay, that will be the substitution we need to perform. But if you remember that u was a dummy variable to introduce 2x, then 2x equals 3 tangent theta. So x will be 3 half tangent theta. So you get the same substitution. X was, so if you replace u, okay, with 3 tangent theta, that is equivalent to replacing x with 3 half tangent theta as in the approach 1. Okay, but some people may feel approach 1 is easier, but but there may be some other students who feel the second approach seems to be easier for them. Okay, so whatever approach is fine. You can eliminate the, you may eliminate the number in front of x squared, or you can introduce a dummy variable for a moment to make the coefficient of this new variable squared is 1. Okay, so either approach is fine, and you need to practice a little bit, and whatever approach is, whatever approach you feel comfortable can be used. So anyway, u is 3 tangent theta, or is equivalently, as I said, x will be 3 half tangent theta. Then dx will be this. So square root of 4x squared plus 9 will be replaced by 3 secant theta. Okay. Then by plugging in these expressions into this integration, if you see, if you replace everything in terms of theta, we can calculate this one, right? I mean, this is what I have. But please note, at this point, you need to be careful with one thing. When you consider this a definite integral, so when the definite integral is considered, actually you need to be careful with the two things. One, you don't have to go back to the expression in x variable. You can just proceed with your, okay, I mean, that means you can just integrate with respect to a new variable. That's the, one merit, that one advantage. And second, you need to be careful with the integral domain. I mean, the upper limit and the lower limit. Okay, let me be careful with the upper and lower limit of the integration. When x is replaced, okay, with some expression in theta, as in this example, this upper and lower limits of the integration, those two numbers, 3 square root of 3 over 2 or 0, those are defining some integral domain for x variable, not theta, right? So when you introduce a new variable, theta, in terms of this, then you need to find appropriate values for theta which correspond to the upper and lower limit of x variable. So when x is 0, when x is 0, the lower limit, then 3/2 tangent to theta must be 0. So that means tangent to theta is 0, and the only theta value between minus half pi and half pi, whose tangent value is 0, is 0. So this will give you only one theta. So the lower limit of this integration with respect to theta will be 0. Now, for the upper limit, when x is 3 square root of 3 over 2, then if that corresponds to 3/2 of tangent theta, then when I remove this 3/2 from both sides, tangent theta will be square root of 3, and the only theta value which satisfies this equation will be pi third. So the upper limit of the integral for the theta will be pi third. So you must be careful. You should be careful with this upper and lower limits of the integration. So if I simplify this integrand, you have only this. Now, for the simplicity, if I replaced tangent with sine over cosine and secant with 1 over cosine, we get this. And I have odd power of sine and even power of cosine. So as we considered, you split this cubic power of sine by sine theta squared times sine theta d theta. And then you keep this cosine theta squared in the denominator. And then this sine theta squared will be replaced by 1 minus cosine theta squared. And if you substitute u for cosine theta, then 1 minus cosine theta will be 1 minus cosine theta will be 1 minus u squared. And cosine theta squared will be u squared. And if u is cosine theta, du d theta will be minus sine theta, so that du will be minus sine theta d theta. So sine theta d theta will be minus du. Okay? And when theta is 0, cosine theta is 1. So this is 0. The lower limit will be replaced by 1 in u variable. And when theta is pi third, the cosine pi third will be 1/2. So this pi third, the upper limit of the integration, will be replaced by 1/2 in u variable. So this is what we have. Now I have negative in front of du, and as you can see, the upper limit of this integration is less than the lower limit of this integration. So if I switch these two numbers, you will introduce one negative sign, and that negative sign will cancel out with the negative in front of du. So you get 3/16 integration of 1 minus u squared over u squared du from 1/2 and 1. Now that is simple because I have 1 over u squared minus 1 du. 1 over u squared is u to the negative 2 power, right? So if you integrate this, you get u to the negative 1 with minus sign. And if I integrate 1, you get u. So I have, do you understand what I'm saying? So u 1 over u squared minus 1 is integrated in terms of du. So 1 over u squared is u to the negative 2. So if I integrate this, you get u to the negative 1 with minus. And then I have 1 here, so I get minus u. Okay. Just a second. Yeah. So yes. So this is what I have. So I have 1/2 and 1. So this is the same as this. So I have 1/2 here. Okay. So if you plug in, you do, oops, I have 3/16 in front. So I have to multiply 3/16 and minus u to the negative 1 minus u evaluated at 1/2 and 1. So if you plug in this, you get this expression. And if we do the math, you get this value. Okay. So the point is, for this problem, this is quite difficult and complicated. You need to notice that you have some value, some positive number 4 is multiplied to x squared. But in the table, we have only x squared, right? Plus or minus x squared in the table, right? So in order to have just 1 in front of x squared, as I said, there are two approaches, okay? You can just take this 4 from x squared. That is my first approach, okay? So you can just eliminate this 4. You can just eliminate this 4. You can just take this away, okay? To move this 1/8 in front, and then you can introduce x to replace 3/2. I mean, you introduce the theta, so by x equals to 3/2 of tangent to theta. That is in the table, right? Or you can temporarily introduce a dummy variable u to replace 2x, so that you have square root of u squared plus 9. And then you can use the trick in the table to change u by 3 tangent theta, or x equals to 3 half of tangent theta. Okay? In either way, you get this expression. This is square root of 4x squared plus 9 will be 3 secant theta. And your dx will be replaced by this. And at that point, as I wrote down here, you need to change the upper and lower limit of the integration, because the initial upper and lower limit, 3 square root of 2, 3 square root of 3 over 2 and 0, those define the limits of the integration for x variable, not theta. So with this new variable theta, I need to find the corresponding upper and lower limit of integration. Okay? So you need to find this. But in this example, that was not the end. Eventually, you have some expression like this, so that if I introduce one more substitution, you have the integration like this. So I need to consider a new upper and lower limit of integration. If I do the calculation, eventually you have something like this. So this example 6 is quite difficult and challenging, right? So please be careful, and please review the slides, and please review what I did, and then please try this example yourself without looking at the solution. Okay, from the scratch. Okay, you can just, with this the problem set on a paper, please solve this, and please make sure you can make every step correctly. And this problem, example 6, is quite difficult, and it is very important. So please review this example yourself. Not this weekend, not before the exam, but today. Okay? So please review this example yourself, especially in example number 6. Okay, so that is what we considered in section 3. Oops, just a second, let me see. What, for example, we need to know? Oh, okay. In the exam, okay. So let me go back to the slides, and so in this example 5, I introduced two approaches, right? So I first considered this. Oops. So this approach, right? And that, with that approach, you got this solution, right? And this will be sufficient. This is enough for your final exam. So if I give such a problem, please use the expression, the substitution in the table, and please plug in a tangent theta, not hyperbolic cosine or hyperbolic sine function. This is just for your information. Okay, so you may consider this, but eventually, as I showed, the expression here, number 2, is identical. It's equivalent to the expression number 1. So the solution 1 will be enough for the final exam. Okay. Anyway, that's what I I can tell you here, and let me go to the next section. Okay, so let me go to the section 4. Now, we want to consider the integration of rational functions. Okay, so what is a rational function? What is a rational function? Rational function is defined by two polynomials. So if you divide one polynomial by another polynomial, that is your rational function. So polynomial number 1 divided by polynomial number 2 defines a rational function. Then what is the domain of the rational function? What is the domain? Any x will be included in the domain of such rational function as long as this polynomial number 2 is not 0 at that x point. If the polynomial 2 is 0 at such x, then this rational function is not defined. I mean, it does not make sense because we have some value divided by 0, which is, right, which is not defined. So as long as the denominator is non-zero, then every x on the real line will be included. Now, we want to integrate such rational function. Okay, so for example, 2 over x minus 1 or something like this. This x plus 5, x squared plus x minus 2, those are polynomials. So if you divide one polynomial by another polynomial, then that will be a rational function. So as I said, x squared plus x minus 2 is split to the product of x minus 1 times x plus 2. The denominator is not 0, denominator is 0 when x is 1 and negative 2. So the domain will be every number between minus infinity and plus infinity except minus 2 and 1. So the domain of such rational function will be the union of these three intervals so that I can avoid the 0 denominator. Anyway, that is a the rational function, and we want to integrate such partial fraction. Okay, so you can read the previous slides if you want. Okay, so as I said, when I say rational function f, then that is defined by one polynomial, say p, divided by another polynomial q. Okay, and we say this f is proper if the degree of the numerator is less than the degree of the denominator. So as an example, if I have x minus 1 over x squared plus 3x plus 2, then this is proper because the numerator is the first degree polynomial while the denominator is a second degree polynomial, right? Or if you have x squared plus 1 over x cubed minus 3x plus 1, then the numerator is the second order and the denominator is the third order. So these rational functions are proper. Okay. But if you have, say, x cubed plus 1 over x squared minus 1, this is not proper, right? Or if I have x squared plus 1 over x squared minus 2x plus 2, it is not proper either because the degree of the numerator and the degree of the denominator are the same. Okay? So when I say proper, then degree of the denominator is greater than degree of the numerator. Okay? So degree of numerator is strictly smaller than degree of the denominator, then we say the rational function is proper. Okay? Now, let me skip this slide. I don't need this one. Now, if if the rational function is improper, that means degree of the numerator is greater than or equal to the degree of the denominator, then we can perform the long division you considered in middle school days or high school days or elementary school days. I'm not sure when you learned this concept in your home country, but we can perform the long division, okay, so that you get some remainder from this long division. And so if you when the degree of the numerator is greater than or equal to the degree of the denominator, you perform the long division to get some quotient s, and qx times s of x is subtracted from px to get some remainder r, such that degree of r is less than, so here if degree of r is less than degree of q, in that case then my p can be written as q times s plus r. So if I plug in this, so if p is replaced by qs plus r, then qs divided by q will give you s, and then you get r over q. So this s will be a polynomial as you expect, right? So s is a polynomial. So if f is improper, then we can always perform the long division so that this improper rational function can be written as the sum of polynomial s plus proper rational function r over q, right? So I can always assume that given rational function is a proper, and then we will develop some the techniques to consider the integration of proper rational function, because as I showed here, if you have an improper rational function, then I can always convert this improper rational function into the sum of a polynomial and proper rational function, and polynomial can be easily integrated. Okay, so we just need to handle the proper rational function. So from now on, okay, so for example, if I have this x cubed plus x over x minus 1, that is improper. So in that case, so if I have x cubed plus x over x minus 1, in that case, I can perform the long division, x cubed plus x. And I want to divide this by x minus 1. Okay, then x cubed divided by x will be x squared. So if I multiply x squared to x minus 1, you get x cubed minus x squared. So if I subtract this from x cubed plus x, then minus with minus x squared will be x squared. And then if you move this x, then you get plus x, right? And then if you divide x squared by x, you get x. So if you multiply x to x squared minus x minus 1, you get x squared minus x. If I subtract this from the expression above, then x squared will be erased, and then you get 2x. The degree of this remainder term, 2x, is 1, and the degree of the denominator is also 1, so they have the same degrees, right? So I need to go one step further. So 2x divided by x will be 2. So if I multiply 2 to x minus 1, you get 2x minus 2. So if I subtract the expression below from the expression above, 2x, then you get 2. Then what does that mean? This x cubed plus x can be written by the product of x squared plus x plus 2 times x minus 1 plus 2. So if I replace x cubed plus x by this expression, x squared plus x plus 2 times x minus 1 plus 2 over x minus 1, that will be x squared plus x plus 2 times x minus 1 over x minus 1 plus 2 over x minus 1. And from the first term, x minus 1 can be cancelled, and you get a polynomial x squared plus x plus 2 plus a proper rational function 2 over x minus 1. So we have a polynomial x squared plus x plus 2 plus proper type rational function 2 over x minus 1. So if I want to integrate this function, I can perform this long division so that we have s of x, the quotient, okay, plus the remainder term, rx, divided by my original denominator, x minus 1. Now, x squared or x or 2 can be easily integrated. And the integral of 2 over x minus 1 is just 2 times the natural log of x minus 1. So we can easily integrate this function. So if you see this improper rational function, what you need to do is you need to convert this into the sum of a polynomial and proper rational function. Okay? And how? You need to perform the long division as I did. Okay? So you need to divide the numerator x cubed plus x. X cubed plus x is divided by the denominator x minus 1 by long division. Okay? So if you forgot this trick, you need to brush up your memories. Now, okay, so what's next then? Okay, I have a proper rational function. Then the next step is to split, okay, the denominator. So the next step is to split the denominator as far as possible. Okay, when I say the factor or factorization of qx, if qx is a polynomial, then this denominator qx will be factored into a product of, okay, it will be factored always a product of linear factors of the form ax plus b type and irreducible quadratic factors. When I say irreducible, that means that cannot, then you have a quadratic factors such as ax squared plus bx plus c type. And when I say irreducible, then that means b squared minus 4ac is a negative. So if you want to split this ax squared plus bx plus c as a product of linear factors, then you need to introduce complex numbers. So for example, in case of x to the fourth minus 16, I can easily factor this product of x squared minus 4 times x squared plus 4. Now, in case of x squared minus 4, I can go one step further to x minus 2 times x plus 2. But in case of x squared plus 4, if you go one step further from here, then probably you need to introduce x plus 2i times x minus 2i. So unless you introduce this imaginary number, you cannot factor this x squared plus 4, right? So we don't want to consider these complex numbers in our class. We want to play with only the real numbers. So within the real numbers, within the real coefficients, x squared plus 4 cannot be factored. So we just leave this x squared plus 4 as it is. So if I have any polynomial in the denominator, you will see that any polynomial will be reduced to the product of some linear factors or irreducible quadratic factors. Okay? Now. Okay? Now, so the next step is, so the third step is to express this proper rational function, okay, as a sum of this type partial fraction, this type function, or this type function. Okay, so please note that when I have ax plus b to the certain power in the denominator, then you must have just a single certain numeric value a in the numerator. When I have certain power of irreducible quadratic factor in the denominator, Okay, I will allow only this linear term, ax plus b in the numerator. Okay, so I will talk about this in more detail after the break. Okay, so let us take a break for 15 minutes and then let me resume, okay, at 10:30. Okay, see you in 15 minutes.